So I sent you another test email through the Canvas system yesterday. So anyone who didn't receive that? Hands up. So everyone received that? Okay, that's good. Alright, so today we're going to have our discussions on the physics of the resistor, metal, interconnects. So in the first lecture on Monday, we talked about that the chip is composed of those transistors, but the transistors talk to each other through the interconnect. And the interconnect actually is made of metal wires, and essentially is a resistor, because metal still has the resistivity. So today we are going to discuss the physics of this metal interconnect. And the reference book chapter from this supplementary reading is the chapter 2, section 2.21. And you can have that as your supplementary reading material. And also, here is another resource for you. And this is the recorded lecture from Professor Asif Khan, who is another instructor for the 3030 in the previous semesters. And he kindly shared the recorded lecture for us. So you can also check his lecture through that YouTube link. Alright, so let's look at this resistor. So we know the interconnect here, as we show the video on Monday. So we have the wafer made of silicon, that is a substrate of the chip. And we have different devices there, and we call those devices transistor. So those are the switches. We're going to have more discussions later. You have a question?
Can you turn the lights off up there? It's kind of hard to read the book.
Oh. So, switch is there. Okay, good. So, those are the transistors. Those are the switches to do the computation. Switch from 0 to 1 or 1 to 0. We are going to have more discussions in the later lectures. So today we are going to focus on this interconnect, which are metal wires, to connect the devices at the top of the wafer. So you may have multiple layers of this kind of wires. So here we see this stack of the interconnect. Actually you have many layers. Today's chip may have up to like 12 or 14 layers of the interconnect. And the bottom ones are the local interconnect. That means the interconnect at the bottom tiers collect the adjacent transistors within short distance. And then the upper ones, which are larger, is called the global interconnect. This is to collect, let's say, two circuit modules which may be far away from each other. Then you need the top global interconnect for the communication. So then you have this kind of interconnect. So any questions? And if you look at the chip layout, this is an example of a full chip design. And here what we show on this figure is a clock tree. So basically, for the digital circuit, you have the clock, and then this clock will be distributed into different locations of the chip. So each logic gate is controlled by the clock. And this is for sequential circuits. So you need to distribute the clock to different locations of the chip through this clock tree, and then essentially through this interconnect. And here is the top view of the interconnect routing for the clock signal. And you see this kind of wires. We have some local wires here, which are short, and also we may have some long wires for global interconnect. So this particular chip is for this AES encryption engine. So AES, is one standard method for encryption. So for example, your password encrypted by AES before you send to the Wi-Fi, right? So you need to encrypt. So then you need some circuit to do this encryption. And in this encryption engine, actually it's a large circuit. It has 120,000 cells. The cells means basic logic gate, like NAND, NOR, or inverter or buffer. So inverter, is not function. And buffer, if you have two inverters, then you are going to have the same signal. Then it's like you buffer the signal. So it's all this kind of cells, and then you have 120,000 cells like this. And in total, you may have this 700,000 transistors in this chip. So you need interconnect to route the clock to those cells. And again, this is the image we showed in the previous lecture. This is the cross-sectional view under the microscope for the Intel's processor. And we see those interconnect many layers. And the global interconnect is wider or thicker because you need to communicate the signals to longer distance. Then you need a larger wire to carry that because of resistance. And then we have the transistors to the substrate. And this is what we have discussed in the on Monday, so I will skip this slide. So here what we want to discuss is that the total distance of the interconnect. Can you imagine for this, for example, Intel's processor, if you measure the distance of the total interconnect on this chip, how long is it? Any rough ideas? Don't look at the numbers on the table. Just a guess. Just a random guess. Like a foot or a mile or what? So if you look carefully here, you will see that. So this is the total interconnect length. Okay, it's in the unit of mile. This is a different generation of the processor, like from 2001 to 2007. The technology node is like 130 nanometer down to 65 nanometer. And here is the number of transistors on the chip. And then this one is the interconnect length. Okay. For today's chip, it's more than 10 miles. If you unroll that interconnect into a single line, then you will have more than 10 miles on this tiny chip. So this is a lot. Any questions here? All right. So let's look at the circuit elements for the integrated circuits. And those symbols for the circuit. And we have the linear circuit elements, like the resistor, capacitor, inductor. And I believe that you have learned those in 2014, like the RC circuit. So those are linear circuit elements. It's linear because, for example, the resistor, the current and voltage relationship is a linear function. So that's why it's a linear circuit. But there are nonlinear circuit elements as well, which are typically used in the integrated circuits. For example, here we have this diode, and we are going to learn more details of diode in the later lectures. Basically, the diode can only pass the current in one direction. So you only pass the current in this direction.
Why is a capacitor considered a linear system?
So because let's say the charge and the voltage is in the linear relationship.
Oh.
Yeah. Of course, if you solve the RC circuit, you may get an exponential function, but still we have to consider that as a linear circuit element. It's unlike the diode. The IV is non-linear. We're going to learn that it's an exponential function. So you only pass the current in one direction. Okay. So this is the PN junction, and then we have this transistor. Okay. And the transistor symbol is something like this. We are going to have more discussions later. But this is the circuit symbol for the transistor. And this transistor is the MOS FET, metal oxide semiconductor field effect transistor, or MOSFET. So this is the mainstream technology today for the transistor. And here we are going to learn the details of those nonlinear elements in the circuit. Maybe you have learned in the 2040 on those linear circuit elements. Here we are going to learn the nonlinear elements. Because those nonlinear elements, especially this transistor, is the basis for the digital computing. You need this kind of circuit. The RC circuit will not work for your digital computation. You need this transistor. All right. If you look at the materials used for building those circuit elements, actually you can classify the materials into 3 groups. The first one is metal, and second one is dielectric or oxide, which is non-conductive or insulator. And the third category is what we are going to learn in more details. It's a semiconductor. Silicon is considered as semiconductor. So the semiconductor is somewhere in between the metal and the dielectric or the oxide insulator. Semiconductor, as the name suggests you, is semi-conductive. Okay, so sometimes it conducts current, sometimes it does not. Okay, so this is somewhere between the metal and the insulator. And if you look at the circuit element we showed earlier, the resistor is typically a metal, and this is very simple. If you have a piece of metal, the metal will have some resistivity, and then you can use that as the resistor. And interconnect use that. So the metal is a resistor. And in the integrated circuit, actually the doped silicon is also a resistor. So if you make the resistor on your circuit, you sometimes use a piece of silicon. If you don't dope it, that means it's pure silicon, it's semiconductor. But if you dope it, we're going to discuss in more details what is doping. So basically you add some impurity into the silicon and you make it conductive. So if you heavily dope the silicon, it will become more like a metal. So you can also use that as the resistor for the circuits. And this is for the resistor. If you want to build an inductor, you can also use the metal, and sometimes you need to make some shape of the wire into this kind of spiral kind of shape to make it as inductor. So it's a metal wire, but you know when the current goes this loop, according to the right-hand rule, you will have some magnetic field associated with the current flow. So then you can make it as inductor. And then for the capacitor or cap, so what is the simplest form for the cap? Any idea? You have the plate capacitor. Essentially, you need to use both metal and the dielectric. So, for example, here you have those shaded region like metal, and you have your oxide in between. So then this is like a plate capacitor. In this case, you need metal and dielectric to make a capacitor. And then the last one is this MOSFET. Actually, you need to use 3 groups. It's called MOSFET because it's metal, oxide, semiconductor, field effect transistor. So you need 3 kind of material to build this structure. So essentially, in this circuit symbol, this side is metal, and then this is a capacitor, so this is oxide. And then the other side, this side is the channel. It's built on the silicon substrate, so it's a semiconductor. So you have 3 kind of material in the MOSFET. So it's more complicated, and we're going to learn in great details about the MOSFET in this course. And for the integrated circuits for digital system, you mostly deal with the MOSFET and the capacitor, and sometimes we consider the resistor for the interconnect. For the inductor, it's rarely used, so we don't even have that for the digital circuit. You don't use inductor. If you talk about analog circuit, for example, your transceiver to receive your signal through your LTE, whatever, wireless communication, the front end may have the inductor as analog circuit front end, but the digital system never uses inductor. Okay, so this is the circuit elements. And today we are going to focus on the resistor, or the metal wire, for the interconnect. So we need to have a deeper understanding of the resistor. I know everybody knows resistor, and everybody knows that equation. Okay, I'll assume. Okay. So what is that equation called? This one? Ohm's law, right? So this is simple. Okay. Ohm's law. So the voltage across this resistor proportional to the current, right? And then this coefficient is called resistance. So everyone knows this. But today we're going to derive something here. This is some, I would say, the macroscopic view of this resistor. Macro. That means large scale. Macro view of the resistor. But actually, we need to think about in the microscopic view, because electrons are flowing through the resistor. So we need to, let's say, derive some equations from the macroscopic Ohm's law to the microscopic electron flow. So we will do that today. So here are some derivations, and I will do it slowly. So first of all, the electric field, okay, by definition, across this resistor is defined as the voltage across this distance. So if you have the distance L, then the electric field, by definition, is the voltage divided by that L. And also the current density is defined as the current divided by the cross-sectional area A of that resistor. Or you think this is a piece of metal, and you have the side A and B, then your area is A times B. That is the cross-sectional area. Okay. So the first thing we want to derive is that, let's do this. So V equals to IR, and then you know the V, you can replace that LE. So you have LE, and then IR. And then the I is also the J times A. So you plug in that, you will have LE JAR. And then you can get J equals to, remove the AR to the other side. Then it's L divided by ARE. And then we define this as sigma. So it's J equals to sigma E. Okay. Some derivation from those equations. So this sigma is called conductivity. This sigma is called conductivity. Sigma is L A